Hello everyone, happy to see you here. Welcome back to my channel, Hi Mathematics. Today we have very interesting and in the same way, this is a very tricky question. 1 to the x equal to 3. And a lot of students might be saying, okay, 1 to the x equal to 3, this is not possible because we know that 1 raised to doesn't matter what a power, like huge power 100, 1000, equal to 1. And how is it possible? 1 to the x cannot be equal to 3. Right now, let's try to solve this question. Let's try to see, maybe we'll have like another solution, another route. So let's try to solve this question completely and step by step. First of all, let's apply natural log on both sides. As a result, we have natural log of 1 to the x on the left side equal to natural log 3. Of course, when we have x right here at this position, we can easily bring this x right here to this position according to a basic log property. Whenever we have expression like natural log, for example, 3 to the power 4, we can write it as 4 times natural log 3. Okay, so and for this, let's write this x behind this point. Okay, so we have x times natural log 1 equal to natural log 3. And right now let's divide both sides by this natural log 1 because we need to find only our x. Let's do this. Let's divide both sides by natural log 1. As a result, what do we have? X times natural log 1 over natural log 1 equal to natural log 3 over natural log 1. So we're going to cancel it from here, and as a result, what do we have? X equal to natural log 3 over natural log 1, and this is our root. But if you look closely, natural log 3, this is a constant, obviously, but natural log 1, this is our 0, so it means that we can't divide by 0, obviously, in terms of our school knowledge, and basically, yeah, so right here we can easily write that no real solutions. And you know, it could be a solution to your school exam. This is absolutely enough for you because no real solution, and we solved this question, no real solution. But for math lovers, I'm going to show you a really interesting approach. There is one really interesting and in the same way important thing. This thing is called Euler's identity. This identity looks like that: e to the power I times theta equal to cosine theta plus I times sine theta. This is our identity. We can easily check it real quick. So for example, let's test this identity. So we have theta equal to 0, for example. As a result, we have e to the power I times 0 equal to cosine 0 plus I times sine 0. As a result, right here, e to the power I times theta equal to 1, cosine 0 equal to 1, and sine 0 equal to 0. So as a result, absolutely great identity for us. And right now, I'm going to show a really important substitution. So let's do that. This substitution looks like that. We have theta equal to 2k pi, and k is z, of course. We are talking about integers. We are talking about equal to 1, 2, 3, 4, and a lot of this case. So right now, let's use this substitution, theta equal to 2k pi. Let's plug in inside this theta. Let's plug in right here. Let's plug in theta equal to 2k pi. As a result, what do we have? E to the power I times 2k pi equal to cosine 2k pi cosine 2k pi times I, not times, like plus I times sine 2k pi. Okay, this is our substitution. And right now, the most important part. Let's see what will happen when k equal to 1. For example, let's see what will happen. So k is equal to 1. Let's see what will happen. So as a result, what do we have? E to the power I times 2 pi equal to cosine 2 pi plus I sine 2 pi. And if you look closely, cosine 2 pi equal to this one equal to 1. Okay, equal to 1. Sine 2 pi equal to 0. Okay, so right here on the right side, we have 1 plus 0 equal to 1. Okay, let's see what will happen next. Let's check when k is equal to 2, for example. So k is equal to 2. As a result, we have e to the power I times 4 pi equal to cosine 4 pi plus I sine 4 pi. And right now, if you look closely, okay, cosine 4 pi equal to 1, yeah, and sine 4 pi equal to 0. So 1 plus 0 equal to 1. So it's really great, absolutely the same expression. So on the right side, we have all the time 1. But let's check once more. For example, k is equal to 3. Let's see what will happen. So k is equal to 3. Equal to, not like equal, let's use this line. So e to the power I times 6 pi equal to cosine 6 pi plus I sine 6 pi equal to, what equal to? Cosine 6 pi equal to 1 and sine 6 pi equal to 0. So 1 plus 0 equal to 1. And I hope you got my minds right here, because it doesn't matter what we are talking about on the left side. On the right side, we have all the time 1. Okay, k equal to 1, all the time 1 on the right side. K equal to 2 equal to 1. K equal to 3 equal to 1. So I hope you catch my minds right now, because we are talking about our left side. So on the left side, we have e to the power I 2k pi. Okay, with this substitution, e to the power I 2k pi equal to 1 all the time. So here's our expression that we really need right now. E to the power I 2k pi, I times 2k pi, equal to all the time 1. We check it. So of course we will have like a period right here. When k equal to 4, we have 8 pi. When k equal to 10, we have 10 pi. Yeah. So equal to 1. Okay, extremely important expression in our case, but with a lot of like restrictions. So k is integer. We are talking about integers. K, we have 1, 2, 3, 4, and a lot of these values, because in this point we have all the time 1. But don't forget about expression in the beginning. In the beginning we had 1 to the x equal to 3, and right now instead of this 1, let's use this expression right here. We can easily do this. We proved before that we don't have real number roots. So right now let's try to work with the complex roots. So as a result, we have e to the power I 2k pi to the power x, don't forget about it, equal to 3. Okay, we look right here at this point, because this is our question. We need to find our x. Right now let's raise this expression to the power x. As a result, we have e to the power I 2k pi times x equal to 3. What are we gonna do next? Let's apply natural log on both sides, like the basic tricky steps right here. So natural log of e to the power I 2k pi x equal to natural log 3, and of course this power will come down right here. So as a result, we have I 2k pi x equal to natural log 3. Okay, and right now the final tricky move, let's divide this expression by I 2k pi. Okay, this one by I 2k pi, and this one by I 2k pi. Why I divided? Because when we cancel this, we have only our x on the left side. So as a result, we have our x equal to natural log 3. Yeah, we have natural log 3 divided by I 2k pi. Of course, k is equal to like 1, 2, 3, like integers. Yeah, we have it right here. Okay, we have restriction about k. This is our imaginary unit, but like for better understanding, we can easily multiply this by I numerator and denominator by I. In our denominator we have I square, so we have minus, because I square equal to minus 1. So as a result, we have the negative sign in the beginning. So x equal to minus natural log 3 times I, and we divide it by 2k pi. But k is not equal to 0, obviously. Yeah, we're gonna write it. So k is not equal to 0. Yeah, k is not equal to 0. K is integer value. K is z, and of course k is our 1, 2, 3, like a pattern, 1, 2, 3. Okay, and this is our solution to this question. Obviously, this is a complex root, because in the beginning we proved that x is not a real number, because we can't divide by 0, and with this tricky approach we have our answer. But to be honest, this is not a general answer, like 100% like our answer in each of these cases. We are talking about a case when k is not k is integer. Okay, we are talking about only when k is integer value, because we prove it for integers, k equal to 1, 2, 3. But what will happen when k is equal to 2.5? We don't know about it. But for example, like a special case, this is a great solution there with these restrictions right here. We have k is not equal to 0, k is integer, and of course we have our answer. This is our complex answer. So let's do this. This is our complex answer. complex root right here, and one and only one root. You can also write your notes about this question down into the comment section, because this is not a popular question, to be honest, because 1 to the x equal to 3, students like don't have this type of question on their school exam. This is like a special question, to be honest, and of course if you have your notes, your comments, you can easily write your notes down into the comment section. This is my approach according to Euler's identity, according to these special cases with k equal to 1, 2, and 3. This is my approach to this question. You can also write your notes. What do you think about it? It's really interesting to exchange information. It's really interesting to see your thoughts about this good question down into the comment section. And thank you for your time. You can also leave a comment what do you think about it, and wish you all the best in your life. Take care of yourself, have a great day, and love math. I think everything will be good in your math. If you're struggling with math or pre-algebra concept, you can easily watch my videos. I have more than 200 videos on my YouTube channel, a lot of interesting questions, like for the period of like 2 years I make this content. So I really hope you watch it, you enjoy it. Of course, it depends on yourself. What do you think about it? If you like it, if you don't like, I really hope I will teach you something, like maybe a lot of things in terms of math, like, or not a lot. I'm happy about it if you watch my videos and you give your response in the comment section. It's really kind of you, and it's really important for me. So thank you for your time. Wish you all the best in your life. Take care of yourself. Have a great day.